All right, so today we're going to learn how we graph the sine and cosine functions and make graph transformations, recognize those transformations. And then on the other side of break, we'll look at the other trig functions like tangent and cotan and secant and cosecant. Any questions or comments before we start? All right. So we're going to start first with just sine x and negative sine x, cosine x and negative cosine x, make some observations. It'll be helpful to think about the unit circle, I think, to help us graph these. And I'm just taking the convenient points, the ones that where we know the coordinates, using those to help us kind of plot the continuous curve. So the sine function is the y-coordinate on the unit circle. So we're just going to plot or keep, mark down what the y-coordinate is at each of these values. So we're just going to fill out the middle column here. At 0, what is sine equal to? Say that louder. 0. And at pi over 4? Just need the y-coordinate. Thank you. And for the sake of plotting, it'll be kind of helpful to have approximations. This is about 0.404. Or it's not 404. It's 707. Root 2 is 1.414, so I get. Okay. At pi over 2? 1, that's the top of the circle. So I'm only taking a few of these points. So I'm choosing to grab these at the pi over 4s and at the extremes. We could get, we could plot all of them and sort of see the smoother curve, but I think this is enough for us to get a decent idea of what it looks like. At 3 pi over 4, sine is over here, so we're still at positive root 2 over 2. At pi, we're on the left side, the left extreme, so the y-coordinate is 0. 5 pi over 4, we're at negative root 2 over 2, and at 7 pi over 4, still at negative root 2 over 2. Somehow I just skipped over 3 pi over 2, but that's negative 1. That's the bottom of the circle. And at 2 pi, we're back at 0. That's back where we started. So if we use these points to plot, notice we're keeping our x values are in radians. So so the x-axis, it marks how many radians our angle theta is, or x. And when I start plotting, I didn't go any further than 2 pi, right? And there's no need to go further than 2 pi because once I get to 2 pi, it just starts over again. So sine is what we call a periodic function. Periodic function just means that there's this repeating behavior. And it's really suffices just to graph one period of any periodic function to understand its behavior everywhere. So we're going to graph one period. Let's plot these points. And if I'm only going up to 2 pi, I just want to kind of comfortably be able to plot all of these points. So I'm going to mark the end of my axis is at 2 pi. And then for all of these trig functions, the first thing I do is I mark up the x-axis by cutting it up into fourths. So here's half of that, which is pi. And this is pi over 2, pi over 2, 2 pi over 2. This would be 3 pi over 2. And then I'll mark the quarters. So pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4. 6 pi over 4, 7 pi over 4. What's the range of values? Like how high up and how far down do I need to be able to go on the y-axis. I'm going to scroll up for just a moment for us to give us a time to think about and answer that question. Yeah, right? Like it's the top of the circle. It's not going to get any higher than 1. It's never going to get any lower than -1 at the bottom of the circle. So I'm just going to mark those values. So all of our y coordinates that we actually plotted were 0, 1, or √2/2, which we said was about 707. So that's like, I don't know, here. And -√2/2. And now what we're going to do is just plot. So at 0, we're at 0. At pi/4, we're at √2/2. At pi/2, we're at 1. At 3pi/2, back down to √2/2. At pi, we're at 0. At 5pi/4, we're at -√2/2. 3pi/2, that's the bottom of the circle. And 7pi/4 at -√2/2. And at 2pi, back to 0. Alex.
I would love to.
So now we have these. Now the sine curve is a smooth curve. This isn't connect the dots. This is try to draw a smooth curve that kind of goes continuously through these points and not a collection of straight line segments. So it does something like this. There's Sine X. Can you guys pass this back to Aiden? So we have different ways to visualize sine. You know, here's a graph of y equals sine x, one period, right, as x ranges from 0 to 2 pi. We also have another visualization of the sine function, which is it tracks these y coordinates. You know, when I think of trig functions, the first image that comes to my mind is usually the unit circle. But the way these are connected is you could just imagine, like let's say I fix this point here, right? I've got a point here. Imagine how this is a wheel, like a bicycle wheel that's free to spin around. All we're doing is starting it now, spinning it around like counterclockwise, and then just keeping track of what that y coordinate is as it goes around the circle. And that's what this graph is. Let's do one more here. Let's fill out this third column, negative sine x. I'm just going to take all of those values that we found in the middle column and change the sign. So of course 0 is unsigned, so that's 0. Negative √2/2, -1, negative √2/2, 0, positive √2/2, 1, positive √2/2, 0. Just flipping the signs, and now we're going to plot these points. So 0, negative √2/2, -1, negative √2/2, 0, positive √2/2, and 1, positive √2/2, and 0. And then draw a smooth curve that goes through all these points. And this one in blue, this is negative sine x. What happened when we put a negative sign in front of the function? How is the blue function related to the black one? It's what? It's not the inverse. Opposite. Visually, graphically, physically, how is it related? Nothing?
Mirrored or opposite?
Mirrored, yeah. In fact, the word we use in mathematics is we say it's a reflection across the x-axis. And if you and that's true for any function, like the graph of f of x versus the graph of negative f of x will just be flipped or reflected across the x-axis. Was that fun? Yeah? Got good news for everybody. We're going to do it again. Let's do it for cosine. So again, we're just going to take the exact same process. Only this time we're doing for cosine, so we're going to track the x coordinates. So that means at 0, cosine x starts at 1. Pi over 4 is root 2 over 2. Pi over 2 is 0. 3 pi over 4 is negative root 2 over 2. At pi, we're at negative 1. 5 pi over 4, negative root 2 over 2. 3 pi over 2 is 0. 7 pi over 4 is root 2 over 2. 2 pi is back at 1. And again, there's no need to go any further than this because once we get to 2 pi, the pattern just repeats. We only need to track what's going on for one period of the function. We could plot these points and then graph the best curve we can that goes through them. Again, the period is 2 pi, so I'm going to put 2 pi near the end here. Cut it up into quarters first and then into eighths. There's pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. The range of values is the same. It never goes bigger than 1 or less than negative 1. So here's 1, here's negative 1, and root 2 over 2 is probably around here. Negative root 2 over 2 is probably around there. So now at 0, we start up at 1, positive 1. At pi over 4, we're down here. At pi over 2, we're at 0. And at 3 pi over 4, we're at negative root 2 over 2. At pi, we're at negative 1. 5 pi over 4, back to negative root 2 over 2. 3 pi over 2, bottom of the circle, so x is 0. 7 pi over 4, at positive root 2 over 2, and then at 2 pi, we're up to 1. Now we're just going to draw as smooth a curve as we can. That goes through those points. The behavior looks different, a little bit different. It's really quite similar. We're kind of looking, a single period of cosine that starts at 0 and ends at 2 pi just looks a little different than sine, but it's really the same. If I kept going, right, if I tracked what was going on at 9 pi over 4 and 5 pi over 2, it would just come back down around and we'd see it's really the same kind of wave. It just sort of starts in a different spot. And again, we have the same kind of behavior where, or we could think of it the same way where, if this is like a wheel that is free to spin around, if I just mark a point and track what it's doing as it spins around, keep track of the x coordinates. That's what this graph shows us. Now we'll just do the same thing for negative cosine x. So we'll fill out this last column by just changing all the signs. And if we plot these out, oops, it's a different color, so there, and we're at negative root 2 over 2, we're still at 0 there, positive root 2 over 2, positive 1, and this looks like this. Probably not surprised to see how, the blue curve ended up looking, because if you throw a negative sign in front of any function, all it does is reflect it across the x-axis. Okay, so we know the effect that the negative sign has in front of the function, and what effect that has on the graph of the function. We're gonna now consider some other changes we might make. We're gonna take a look at the graphs of 2 times sine x and 1/2 sine x. We know the basic kind of what that sine curve looks like. So what I'm doing now is I've just shortened the list of values, and I'm just looking at the extremes, at the quadrants. So sine of 0 is 0, so 2 sine of 0 is still 0. Sine of pi over 2 is 1, so multiply that by 2, we get 2. At pi, we're still at 0. 3 pi over 2, we're at negative 2, because 2 times negative 1. And at 2 pi, back to 0. If I were to do the same thing for 1/2 sine x, I'm just going to take the values of sine x at these values, cut them in half. The same values for sine x, not 2 sine x. So cutting those in half would give us 1/2, 0, negative 1/2, 0. Still just graphing one period. So I'm going to mark out the 2 pi and then cut it into quarters. Oops. Now, in order to graph both of these curves, I need to accommodate the values for 2 times sine x. So I'm going to go up to 2, down to negative 2. So there's 1, which means 1/2 is about here, negative 1/2. So if we do the 2 sine x, this looks like this. Again, we're drawing the sine curve that goes through these points, not a collection of straight line segments. So this is going to look kind of like this. And if I plot the points for 1/2 sine x, it looks like this. The overall behavior of the function is the same. We still get this sort of wave curve for the function. What changes? The amplitude, right? Like just how high, like where its crest and trough occurs. Just sort of stretching it out or compressing it. But it still fits in the same period, right? It's the period is still the same length. So that value that's inside describes, or that's outside, right? The factor outside describes the amplitude. Amplitude is always a positive value. It really is just a measure of how far it strays from what I like to call like the equilibrium, like this where it zeroes out. So even if it's reflected and we have a negative outside there, the amplitude is still a positive. It's just a measure of how far you stray from the equilibrium. And here that is given in the definition. So the amplitude is the absolute value of A, if we're looking at A times sine x or A times cosine x. So we have kind of an approach here to graphing these functions. This time when we graphed these, I didn't bother with the pi over 4 values, right? We kind of know the basic wave curve what it looks like. So I just wanted to keep track of where is it at 0, where does it meet the peaks and valleys, and then just draw the curve that fits that. When I sketch that curve, I mark out the end of a period, and then I cut it up into quarters because that's where those zeros and peaks and valleys occur. And plot just a handful of points, not too many. I don't think we spent terribly long plotting out these curves. there's because these functions are periodic and they have kind of predictable behaviors, we just have to keep track of a couple of important facts about the function, and then we'll know what points to plot, and then we'll just fit our curve, whether it's the sine or the cosine, within those points. So if I wanted to sketch a graph of minus 3 cosine x, first of all, what's the amplitude here? Yep. Positive 3. That tells me that when I graph this, I need to accommodate values that go up to 3 and as far down as negative 3. I'm going to mark out going out to 2 pi and cut that up into quarters. Now, it's a negative 3 out in front. That negative sign tells me that it's reflected. So I'm basically going to take that graph of negative cosine x that we did. That's one that starts out at negative 1. And I'm just going to stretch it out. So it starts at negative 3 and goes as high up as positive 3. Cosine is the function that starts at one of its extremes. So at 0, now I'm going to be down at negative 3. And if I know what function I'm graphing and I know where it starts, then the rest of the points practically fill themselves in. This starts at the lower extreme. Where is it going to be at pi over 2?
Right back.
Say that again?
Right back at the extreme.
Oh, at pi over 2?
Oh, it was
Yeah.
2 pi.
So at 2 pi, I agree, it'll be back at the lower extreme.
0.
It'll be at 0. Then at pi, it's going to be up at the upper extreme. Then back at 0. Then back at the lower extreme. And this is what it looks like. It's almost as if we just took the graph of minus cosine x that we already did, and then just erased the 1 and negative 1 and wrote 3 and negative 3, which is essentially all we did. Okay. All right, so we know how to change the period, or we know how to recognize what the period of, or not period, the amplitude of the function based on that coefficient in front, and also to tell whether it also includes a reflection of the graph, as this one did. Now we're going to talk a little bit about period. So the period is basically how long it takes until the pattern starts to repeat itself. And for us, when we're graphing, when we're thinking about tracking just plain old sine x or plain old cosine x, we just think about having one go around the circle, right? Because one go around the circle is what you need to get all the values of those functions and the pattern established. So you don't need to plot any more points. So one go around the circle is always 2 pi. We can actually adjust the period depending on how we write that function out. And when you look at a graph, I guess, it's sort of, I usually use either a peak or a valley, but it's like you take the same corresponding point in the pattern and see where it starts to repeat itself. So I almost always use a peak or a valley. There's only one peak that we could see in this period, but for this graph, we do have 2 valleys, and this period is 2 pi. That goes from 0 to 2 pi. Now for just sine x and just cosine x, 2 pi radians is what we need to get one go around the circle. We can change the period of the sine and cosine functions by adjusting the coefficient on x inside the argument, like inside the function itself. And the period of those functions is 2 pi over b. So whatever that coefficient is, you're going to take 2 pi and divide it by that coefficient. That gives you the period. And here's why. Here's why. If we were to consider graphing, and we're actually going to do this on the next page, sine of 2x. And I'll talk about that procedure or strategy in a second, but if I think about graphing sine of 2x, what that does is it says, you know, when we think about sine x, we think, okay, like we're spinning this wheel around, so it has one go around the circle. 2 times x says spin it around twice as fast. And you only need half the time to do that. So the period of this is going to be 2 pi over 2, or just pi. If x ranges from 0 to pi, then 2x is going to range from 0 to 2 pi, and you'll get all the values repeated, or, you know, once around the circle. So we're going to graph sine of 2x and sine x on the same set of axes. So we'll note that with sine of 2x, the amplitude is 1, the period is 2 pi over 2, or just pi. For sine x, and I'm writing down both of these things first before I start, because I need to accommodate both of the range of values, you know, and both periods on the same set of axes. So here the amplitude is still 1, and the period is 2 pi, which is, you know, the same as 2 pi over 1 if we think about the coefficient on x just being 1 here. I'm marking it out because, first of all, they have the same period, so I know that 1 and -1 will work for both. But they have the same amplitude, so I know that going up to 1 and going down to -1 will work for both of them. When it comes to the period, I have to make sure I can accommodate the longest period, and then I'll just fit the shorter period within that. So I need to go as far up as 2 pi. I'm going to cut this into fourths, just like we've been doing. That's pi. This is pi over 2. 3 pi over 2. So maybe actually let's just plot sine x first. Sine is the one that starts at 0, and it's not a negative sign, it's positive sign, so it starts at 0 and goes up. So at 0, pi over 2 are at the top, pi over at 0. There we are. Now for sine of 2 pi, its period length is pi, so it'll complete a full cycle by the time it gets here. But I want to cut that period up into fourths, so I'm going to do the pi over 4s. I'm going to mark out the pi over 4s here. So pi over 4, 3 pi over 4. Maybe I'll even go further, 5 pi over 4. 7 pi over 4. So again, it starts at 0. Now it reaches the peak at pi over 4. It's down at 0 again at pi over 2. At 3 pi over 4, it's at its lowest point. And at pi, we're back to 0. So I'm taking the same behavior, I'm just compressing it kind of horizontally to fit into this shorter period. And if I want, since I've graphed a whole period of sine, I could just extend this and graph another period of sine of 2x. I don't have to, but you know, it's enjoyable. Questions? Okay. You want to do another? So, we're going to sketch the graphs of cosine of x over 2 and cosine x on the same set of axes. So the first thing, so with cosine x, right, we know that the amplitude is 1 and the period is 2 pi. We've already graphed that. Before I start graphing or plotting anything, I'm going to mark down the same information for cosine of x over 2. And with cosine of x over 2, I'm actually just going to rewrite that as 1/2 x, because I want to be able to see what's the coefficient on x. And if it's x over 2, the coefficient is actually 1/2. The amplitude is still 1. But the period is 2 pi divided by 1/2, which is 2 pi times 2, which is 4 pi. So when I mark out my period, I have to accommodate the longest period, so I'm going to go out to 4 pi. The period of just cosine x is 2 pi, so I'm going to cut that up into quarters. So I'm going to have the pi over 2 and the 3 pi over 2. Maybe we'll graph cosine x first. The amplitude is 1 for both of them. And cosine is the one that starts at the peak, right? It's not a negative cosine, so it actually starts at the top value. And then at 0 at pi over 2, at pi it's -1, and at 3 pi over 2 it's back to 0, and at 2 pi back at its peak. For the 1/2 x, we marked its period out at 4 pi, and we're going to use the quarter marks, which are at pi, 2 pi, 3 pi, 4 pi, and use that to graph, to plot our point. So it starts again at the peak, so at 1. Now it's at 0 at pi. At 2 pi, it's at -1. At 3 pi, it's back to 0. Oh. Yeah, and at 4 pi, it's back up at the peak. Right? So it looks something like this. Fun? When the coefficient is 1/2, that's sort of like saying you can take that wheel, spin it around, but spin it around half as fast. It's going to take twice as long for it to make one full go around the circle. Let's do another one. Let's do one more, and then we'll talk about phase shifting. Questions before we do that? Let's sketch the graph of -2 sine of 3 pi x. What's the amplitude? 2. And the period? How do I find it? Let's do that first. Yeah, so I'm going to take 2 pi divided by b, which for us right now is 3 pi. So we get 2/3. That's the period. The amplitude is 2, so I'm going to mark that as 2 and positive 2 and -2 on the y-axis. The amplitude is 2/3, so I need to go out to accommodate one full period. It goes from 0 to 2/3. I'm just going to mark near the end of my x-axis 2/3, and I'm going to cut that up into fourths. This part, like marking the x-axis, is something that sometimes people find challenging. So the half, the first thing I do is I get the halfway mark. That's usually pretty easy. So half of 2/3 is 1/3. And then half of 1/3. If you're cutting a fraction in half, all you need to do is double the denominator, so half of that is 1/6. The challenging part, what people really struggle with, is this guy right there. So if you're cutting it up into fourths, we're cutting it up into equal fourths. So here's 1/6, 2/6, 3/6, or 1/2. Where does the sine function start?
Zero.
At 0. And from here, where do we go? Where are we going to be at 1/6? Say that again?
2.
No.
Maybe
-2, because there's a reflection, yeah. And then, you know, so it starts at 0, goes down. The rest of the points practically fill themselves in. We're back at 0, then we're up at our peak, and then down at 0 again. So it looks something like this. When you graph a sine function on the calculator, I mean, sometimes people like to use the calculator to see if they got it right. And it can be hard to tell sometimes. First of all, you have to have your calculator in radian mode, right? That's going to make a huge difference. But second, if I were trying to figure out if what I did was right, I'd want to make sure I set my window settings to reflect like this information that I marked at the top and the bottom, and then see does it look the same then. So if I were to check this on the calculator, so I'm plugging in -2 sine of 3 pi x, whoops, 3 pi x. So first of all, if I just hit graph right now, let's see what happens. Oh. That's dissatisfying. There's the standard window. That's what it looks like. It doesn't look anything like what we graphed. So you'll just note my calculator is actually in degree mode, so I'm going to change that to radians. Next, what I'm going to do is just set my window. My x really just needs to go from 0 to 2/3. The scale, that's how often it makes a little tick mark. I want to use that, like when we cut up the R period into quarters, I want to use that 1/6, that first quarter, like I want to use that as my scale. 1/6. Y min and Y max, so -2 to 2. And now if we look, that's a perfect fit. And that's how I can tell. There's my confirmation that I've got it. Want to talk about phase shift? Okay. So we know if we're changing up the amplitude if we see like a coefficient other than 1 or -1 in front of the function. We know if it's reflected if we see a negative sign. We know if we're changing the period because we see a coefficient on x inside the function itself. A phase shift is the same thing as just a horizontal shift. It just slides the curve like left or right. And we can tell that we have a phase shift if we have if we're adding a constant inside the parentheses, inside the function itself. So the coefficient on x, like that number there, tells me about the period of the function. If I'm adding a number after that or subtracting, that talks about phase shift. And so I can tell there's a phase shift there, but you don't just take this number c and say, oh, there's my phase shift. What you have to do first is whatever this coefficient is on x, you have to factor it out. And once you're looking at it, so the point at which you could just point to the number and say, there's my phase shift, is if that number is being added or subtracted just from x, not 2x or 3x or -5x or whatever, but just plain old x. So in the parentheses here, we have just 1x plus c over b. That's our phase shift. So when I've got a function, I can tell there's a phase shift. I just make sure that the first thing I do, factor out that coefficient of x. It lives inside the function, right? I mean, there's still our factor of b right there, right? It's inside the sine function. The same is true for cosine. I wrote it out with the sine function here, but the same is true for cosine. The same is true when we'll work with secants and cosecants and tangents and cotangents. So the phase shift is the value c over b. It moves to the left if c over b is positive. That's kind of backwards from what we think. We think the positive direction is over there. But if it's a plus a number, it's going to move to the left. If we're subtracting a number, it moves to the right. So let's sketch a graph of this function, 1/2 sine of x plus pi over 4. What's the amplitude? What? 1/2. And we'll just note that there is no reflection because it's a positive 1/2 there in front of the function. What's the period? 2 pi because it's a 1x. And here, we don't have to worry about factoring anything out because it's already a 1x, right? In the parentheses, I just have plain old x plus pi over 4. So when I write out what the phase shift is, and this is important, I'm going to write out the amount and the direction. So, pi over 4, left. You could write left or right, or you could use an arrow. Either is fine. But I don't want to see like somebody say, oh, it's a plus pi over 4, so the phase shift is negative pi over 4. Like, I don't want you to indicate it with signs. I want you to be descriptive, like visually, like describing what it does. So the period is 2 pi. Now, here's how I always graph these with a phase shift. I first just graph the function that doesn't have the phase shift. So I'm going to go out as far as 2 pi. I'm going to mark out, like I don't have to graph it like, it doesn't have to be perfect. And I'm actually going to graph it kind of lightly because I want the other one to stand out. Oops. Our amplitude was 1/2. So I'm going to have 1/2 and negative 1/2. And I'm just going to do this in gray. So sine starts at 0 and goes up. Sometimes if I'm doing it on paper, I'll kind of just draw it dotted or something. But this one is 1/2 sine x. Now what I need to do is move this to the left by pi over 4 units. So I'm going to make new, I think of these points that we put as like my anchor points, right, that I fit the curve around. I want to move each of these points to the left, pi over 4, just get new anchor points, which is easy enough to do. The first one here is at 0, so that will be negative pi over 4. If I move the pi over 2 back, I'm at positive pi over 4. At pi, we're at 3 pi over 4. Moving 3 pi over 2 back, we're at 5 pi over 4. Moving 2 pi back, we're at 7 pi over 4. And really, if you're having a hard time coming up with what these values are, just do the subtraction. Just 2 pi minus pi over 4, get a common denominator, and it's 7 pi over 4. So now I'm just moving each of these points back. And I'm going to fit the same curve. How's that? Okay, let's do another. We're going to graph -3 cosine of 1/2 x minus pi over 8. So what's the amplitude? The amplitude is 3, and there's also a reflection. I'm just writing that down so I don't forget later on. What's the period? Or how do I find it?
It's like 4 pi because 2 pi over.
Yeah. Yep.
Over 2.
Good, right? 2 pi over b is 2 pi divided by 1/2, which is 4 pi. Now for the phase shift, we're going to do a little factoring. So here's our function, -3 cosine of 1/2 x minus pi over 8. Excuse me. So I want to factor out the 1/2. When I do that, obviously the first term is just x minus, and what's what, yeah, pi over 4. Right, we were trying to find what's the value that I cut in half. You know, if I'm factoring out the half, then what goes here is whatever value I have to cut in half to get pi over 8. And that would be pi over 4. Alternatively, like if you're ever struggling with that, like figuring out what you end up with when you factor that out.
B is just the coefficient for x, so you can kind of just do it as a fraction.
Say that again?
B for the coefficient of x in the first part is just under it to factor it easier.
Yeah, I mean, depending on what the number is and what each of the two numbers are, sometimes people struggle with that. So if you're ever wondering, I mean, you can always just set up the equation. This, whatever goes there is 1/2 times something gives you pi over 8. It'll always end up being this number, you know, in this case pi over 8 divided by 1/2, right? C over B. So the phase shift. Now we can recognize that phase shift is pi over 4. What direction? To the right. I'm going to keep that in mind when I'm plotting out the end of my period, because I need there to be room to move this graph to the right. So I don't want to have my 4 pi take up all that space, because I have to be able to move it over. I don't have to move it over that much in comparison. 4 pi is quite large, and we're just moving it pi over 4 units. But I'm going to leave some space. So there's 4 pi. I'm going to cut this up into quarters. 2 pi, pi, 3 pi. I need to go up as far as 3. As far down as -3. And like before, I'm going to first just graph it without any phase shift. So this is the cosine, and it's a negative cosine. So it starts down at the bottom and then moves up through 0, reaches its peak, back down to 0, back at the bottom. Now I need to find my new anchor points for this function. So I'm going to take each of these other anchor points, which were at 0, pi, 2 pi, 3 pi, 4 pi, and just add pi over 4 to all of them. 0 plus pi over 4, that's the easy one. And then I also want to make sure that on the graph where I plot it seems reasonable. So like at pi, halfway, that's pi over 2. Half again is pi over 4. So pi over 4 is really just like this short little distance here. And if I move pi over 4 beyond pi, that's 5 pi over 4. Pi over 4 plus 2 pi. Let's see, 8 pi over 4 plus pi over 4 is 9 pi over 4. 3 pi is 12 pi over 4. So that's, if I add pi, I'll get 13 pi over 4. And 4 pi is 16 pi over 4, so when I add pi over 4, I get 17 pi over 4. And I'm just moving each of these points over. And there's -3 cosine 1/2 x minus pi over 8. The one we did in gray is just the one without the phase shift, so that's -3 cosine 1/2 x. Questions? Okay. All right. So that's as far as I wanted to get today. We'll pick up after break and graph the other trig functions, and yeah. Enjoy. You don't have a test to worry about over the break. Like, that's nice. Maybe, if you can fit in some time to practice some of these problems. We'll have a quiz on the Thursday that we get back. That'll include some of this graphing stuff and what we cover on Tuesday.